Lecture 11, Prescriptive Analytics, Linear Programming, Part 2. In this part, we are going to have the problem of gasoline blending. This is a problem in oil refineries, and in oil refineries, crude oil is processed to produce gasoline and or diesel fuels. Here we assume that we are producing three products: super gasoline, regular, and diesel gasoline. Okay, and also we assume that we have three types of crude oils, and we call them as 1, 2, and 3. So by mixing these three crude oils, we can produce the gasoline: super, regular, and diesel gasoline. Okay, and each product is distinguished by its octane rating. So the difference between super, regular, and diesel is the quality of fuel in terms of octane rating, and also the iron content. Okay, so the crude oils also have their own octane ratings and iron contents. Okay. In this table, we have the characteristics of the products and also the crude oils. So the produced gasoline should meet these standards. For example, the super gasoline should have at least 10 rating on the octane rating, and the iron content should be no more than 1. For regular, the octane rating would be at least 8, and the iron content no more than 2. And for diesel gasoline, the octane rating at least 6, and the iron content no more than 1. And here we also have the octane rating and iron content for the crude oils. Okay. In order to formulate the problem, first we need to define the decision variables. Let's define the decision variables in this form: S1, S2, and S3. Here, S1 means we are going to use crude oil of type 1 to produce the super gasoline. S2 using crude oil type 2 to produce super gasoline, and S3 using crude oil type 3 to produce super gasoline, and same for the regular gasoline and the diesel. Okay, D1, D2, D3. So as you see here, we would have 9 decision variables, right? So for the constraints, the first constraint would be having an equation for making sure that we are meeting the standards of octane rating and iron contents. So for for the octane rating of produced gasoline would be the weighted average, of octane rating and iron content of the crude oils that have been used to produce that product. Okay, for example, for super gasoline, if we are using all three types, the octane rating of crude oil 1 is 12. So let's say, so in that case, we will have 12 times S1 plus, and the octane rating of crude oil type 2 is 6. So 6 times S2 plus, and the octane rating of crude oil 3 is 8. 8 times S3, and then if we divide this by S1 plus S2 plus S3, this would be the weighted average of octane rating for super gasoline, and this should be equal to 10. Okay, so this would be the average, and same as this, we would have same constraint for the iron content. Okay, so here instead of having equality, we can have greater than or equal to 10. So we are saying, since we have at least there, so the octane rating would be at least 10 here for the super gasoline. But for the iron content, we would have the same, but since over there it says no more than 1 or no more than 2, we would have the inequalities in less than or equal 4. Okay, and so those would be our constraints. And for the objective function, we want to maximize the profit. Okay, so the profit would be the difference between the revenue and the cost. So let's consider one of the products like the super gasoline. So each barrel of super gasoline is going to be sold by $70. So it would be 70 times S1 plus S2 plus S3. This is the total production of super gasoline, right? This is our income. And but when it comes to the cost, so we have the same terms for other products, and then we have the cost terms. So for crude oil type 1, the cost of each barrel is $45. So here we would have 45 S1 type 1 used to super gasoline, and then R1 type 1 crude oil to produce regular gasoline, and D1 type of 1 of crude oil to produce diesel gasoline. So this would be the total amount of crude oil type 1 that we are using to produce the products. So this total amount should be multiplied by its cost, which is 45. And again, same terms we would have for other crude oil types. So this by this formulation approach, we can formulate our problem in terms of a linear programming model. Okay. Here we have more constraints. The company can only buy 5,000 barrels of each type of crude oil. So here, for example, again for crude oil type 1, we have S1 plus R1 plus D1. This is the total amount of crude oil type 1 used to produce the products. So this should be less than or equal to 5,000, right? And again, same constraint we would have for other types of crude oil. And also we have another constraint that and can process no more than 14,000 barrels total of crude oil. So that means the sum over all 9 decision variables, S1 plus R1 plus D1 plus S2 and so on, this should be less than or equal to 14,000 barrels. Okay, so now by having these constraints and the constraints and objective function that we had in the previous slide, we have our linear programming model, and we can implement this in R and use the LP-Sol or LP-Sol API package to obtain the optimal solution. Okay. The optimal solution obtained by obtained in R is this. So as you see here, we have the amount of regular gasoline, the amount of super gasoline, and for the diesel, it's all 0. So in the optimal solution, we are not producing diesel gasoline, but we are producing regular and super gasoline, and the optimal objective function value is $375,000. Okay, so now suppose we have estimated the demand data. Again, we can use the predictive models here to estimate the future demand. So this is our estimation here. The demand for super gasoline would be 3,000 barrels. The demand for regular gasoline, 2,000 barrels, and the demand for diesel, 1,000 barrels. So now we want to add these constraints in our linear programming model and resolve it again to find the new optimal solution. So here we need to add 3 more constraints. So for example, for super gasoline, we would have S1 plus S2 plus S3. This is the total production of supergasoline from the three types of crude oils, right? So this should be less than or equal to 3,000, right? And again, same, we would have same constraint for the other two products, okay? So here we have the new optimal solution, and as you see here, we are not using the crude oil type 2, we are just using crude oil types 1 and 3, and also we are producing all three products, okay? Yeah, regular gasoline and super gasoline and also diesel one, okay? And the optimal objective function value here, it would be $150,000, so it's much less than the previous optimal objective function value, and this is because we are adding three more constraints to our linear programming model. So anytime that we have more constraints, the solution could be worse than before, okay? So here, if we want to have some discussions, we can say we may add other considerations in our model, like the cost of production or the cost of labor, or other contaminants to consider in addition to iron, and also maybe other quality considerations in addition to the octane rating, okay? When we solve a linear programming model, we can obtain the shadow prices or dual values regarding to our constraints. Here, for the last three constraints about the demand, the shadow prices or dual values are 29 for the demand constraint of super gasoline, and 27 for regular gasoline demand constraint, and 9 for the diesel one. So that means if we could add 1 barrel to the super gasoline, then we would have $29 more profit in our objective function, okay? So yeah, the shadow prices are somehow the value of those resources. Here, since we have a constraint on the demand, so if we could increase the demand, we can make higher profit. And but by how much, these numbers are telling us the amount that we can increase in the objective function value, okay? And another thing that we can have here, the allowable increase, which is coming from the sensitivity analysis. Here we are going to see the right hand side, I mean the right hand side parameter. Here we're talking about the demand constraint, so the maximum demands, those maximum demands, how much they can be changed in order to have the same shadow price. I mean, the dual values wouldn't change in that range of change of the demands. So here we have these numbers. If the super gasoline demand increases by 1,250 barrel, the shadow price of 29 would be valid, and or for regular gasoline, it's 2,500 barrels. And by having that much increase, still the $27 as the shadow price of this constraint is valid. And for the diesel one, it's 1,250, okay? So by having the shadow prices, for example, for the super gasoline demand, we do have 29. So that means if we can increase 1 unit of demand for super gasoline, that 1 unit increase in demand would increase the objective function or total profit by $29. So this is the meaning of or interpretation of the shadow prices. We can use the shadow prices in our other decision makings, like which type of gasoline should the company advertise to increase demand. So here we are, if we assume that the cost of advertising be $2 per unit increase in demand, then we see that the shadow price of super gasoline is higher than the other ones, so it's better to focus on increasing the demand of super gasoline. So we will run promotion plans, advertising plan for super gasoline. Okay, or we can use the allowable increase, I mean the sensitivity of the right hand side parameters for our analysis, like how much additional profit would the company gain if the super gasoline demand increased by 500 barrels. So in that case, since our shadow price is 29, so 500 times 29 would be the amount of increase in our objective function, or total profit. And same question for 1500. If we increase the demand of super gasoline for 1500, since the allowable increase for super gasoline was 1250, and now 1500 is beyond that allowable increase. So by this amount of increase, the $29 the shadow price is not valid anymore. So this says we need to rerun the algorithm. I mean, we need to resolve the model in order to obtain a new optimal solution. Okay, so yeah, if we have changes in the range of allowable increase, we don't need to resolve the model, and by having the shadow prices, we can obtain how much that increase in the right hand side will impact the amount of objective function. But if the increase is beyond that range, we need to resolve the model in order to obtain a new optimal solution. Okay, thank you.